Hi, we're the University of Alaska Fairbanks Design Build Fly Team. I'm Zach Barnes. I'm the president and aerodynamics design team lead.
I'm Elliot Blair, the vice president and electrical team lead.
I'm Zion Alioto. I'm the secretary and the mission team lead.
Our aircraft was designed to fit within the constraints of the rules as closely as possible, giving us a wingspan of 60 inches. We then decided on a maximum gross weight of 24 pounds, which meant that we would need a 12-inch cord for the wing. The tail was chosen to have an 8-inch cord for both horizontal and vertical stabilizers, and a span of 24 inches was chosen for the horizontal stabilizer, with half that for the vertical stabilizer. In order to maintain stability, the tail of the aircraft was placed 33 inches from the leading edge of the wing. The main fuselage was then chosen to be roughly centered on the wing and stretch 40 inches long. The fuselage would also have as large an internal volume as possible to contain as many sensors as we could. The empty aircraft, which is the Mission 1 flight configuration, has a gross weight of 12 pounds, lighter than predicted by about 1 pound. In the Mission 2 configuration, the aircraft will weigh 21 pounds, assuming a cargo of 18 sensors and the winch. This gives a safety margin and allows easy adjustment of the CG. Finally, the Mission 3 configuration weighs about 12.5 pounds. Our plane has a carbon fiber frame with laser-cut balsa ribs and bulkheads forming the shape of the aerodynamic surfaces. 1/8-inch balsa stringers are laid between the balsa ribs to support monocoque covering. This monocoque covering is then used to form a smooth skin.
The control architecture of our aircraft consists of an FrSky R9 900 MHz radio, Maytech 405 wing flight controller, and Corona slim wing metal gear servos. These components were chosen for RC link stability, configurability, and reliable performance. Additionally, the black box recorder of the flight control board provides invaluable diagnostic flight data. The propulsion system consists of two 3,250 mAh LiPo batteries, which fuel dual motors equipped with 18-inch propellers. The batteries were chosen to provide the maximum stored energy allowed by competition rules, while also providing a peak power output rated at over 27 kilowatts. The KDE 4213XF 360 kV motors were chosen for their high power output capabilities and lightweight. KDE XF UAS 55 amp ESCs were used for their compatibility with the ADAS LiPos used and their peak current rating of 95 amps. This propulsion system was designed to produce maximum thrust, providing a high payload and towing capacity.
In order to determine the optimum performing design in accordance with the rules, a figure of merits design session was held early in the design phase. A sensitivity analysis was also performed to determine which mission should be prioritized the highest. For major individual design decisions, trade study analysis was performed to determine the most functional and practical choices. As an example, the design choices for the propeller were performed with estimated thrust, current draw, and efficiency in mind. Our team selected the 16x7 propeller, providing excellent static thrust and able thrust characteristics at 75 km per hour, while maintaining an efficiency of over 80%. During physical testing of the propellers, our data showed that it coincided closely with our estimated results. The maximum thrust observed from one motor was 4.5 kilograms and max current draw of 34 amps. With the design analysis chosen, the plane complied with the rules and was optimized for Mission 2. Drag calculation, propulsion performance, and the course layout were used to determine the expected mission performance. For an estimated cruise speed of 65 miles per hour and a 2,500-foot-long course, a 30-second lap time is expected. This gives an estimated flight time of about 1.5 minutes for Missions 1 and Missions 2, and an overall time in the air of about 2 minutes. For Mission 3, the same cruise speed is expected, which allows a total of approximately 20 laps to be completed.
Okay, good. And then turn on the lights. Okay, so turn it off. And then reel it back in. Before it starts, before you get the full throttle, just break it loose from the. Come on. Whoa. Oh. Oh.
Our primary suspect for the premature landing of the plane is the last-minute addition of skis for landing gear, which were added due to excess snow coverage. The skis do not have end stops, thus were able to move freely, creating disproportionate drag beneath the plane, causing a downward spiral.